So when we had Maxwell's equations coming out, we knew there was that paradox that had to be resolved, that we resolved on day 3 of this series. Well, there were similar issues already existing that Einstein didn't even have his sights on. The fact that general relativity resolved them was support for the theory of general relativity, but it was not one of Einstein's goals when he developed the theory. One of them was the orbit of Mercury. Most orbits are not perfectly circular. In fact, we have yet to find a perfectly circular orbit in nature. And Mercury's is a little more elliptical than others. I've exaggerated here in this diagram. Mercury's orbit around the Sun is not as spread out as this is. But as it came around the Sun, there's what we call a precession in the orbit. Now, you may have played with tops as a child. As the top is slowing down, you might notice it starts to precess. So it starts spinning around an axis like this, and the top goes around in a circle, and the point at the bottom goes around in a circle. So these are spinning around and spinning around. That is what's called precession. There are actually tops that are very carefully designed. When they start precessing, they will actually flip over and start spinning the other way. If you could track one down, I recommend it. They're kind of cool to play with. But Mercury's orbit did the same thing. So it wasn't this closed loop like we usually imagine. Instead, it's more of a floral pattern. So when it came around, it didn't come right back to where it started. So it does what we call precession. So Mercury's orbit spins around like this. And I accidentally pushed a button that undid that all. Grumble. So there we go. The orbit is precessing. And while Newton's laws did predict a certain amount of precession, they were seeing more precession than they should have. So Mercury's orbit was rotating around the Sun faster than they could have predicted. But Einstein figured that out. Once you incorporate acceleration, he realized that we were in a non-Euclidean space. We call certain spaces Euclidean, named after Euclid. In around 500 BC, Euclid really gave birth to modern mathematics with what he called the 13 books of the elements, with 4 axioms and 10 or 12 definitions. He set out things like points, lines, parallel lines, and he described everything that we learn in geometry between kindergarten and grade 12 plus more. Pythagorean theorem, you name it. But he started with just the bare minimum and built everything else from those axioms. That's the way math still works today. An axiom is something that we arbitrarily consider to be true. We cannot derive it from scratch. That is one of the ideas we have to impose on the system. One of the goals of mathematics is to minimize the number of axioms we need to build our system. Euclid did this about 2,500 years ago. And that stood almost unchanged until the 1800s, when non-Euclidean geometry was born. So Euclidean geometry describes everything you could do when your axes are straight. Non-Euclidean geometry talks about what happens when your axes are not straight. Let's do a quick example. We have long been told that the 3 angles inside any triangle will add up to 180 degrees. In any Euclidean space, this is true. But in non-Euclidean space where the axis curves, it doesn't make much sense to talk about straight lines. Instead, we talk about geodesics, which are the straightest possible lines in that space. Let's say your space is the surface of a sphere, like the Earth. Imagine you start at the North Pole and you walk south on the straightest path you can. When you reach the equator, you turn 90 degrees, you walk a quarter of the way around the Earth, and then you turn 90 degrees and you walk back to the North Pole. We have just made a shape that is built of three lines that are as straight as they can possibly be in that space. This is a triangle with three right angles. The interior angles add up to 270 degrees. That is only possible in a non-Euclidean space like the spherical, roughly, surface of the Earth. And Einstein's theories realize that the space that we're in is non-Euclidean. So we can no longer consider all of reality as having straight lines. If you have something like the sun, which is a big source of gravity, well, that sun is going to warp and bend the lines towards it. So this is why we start talking about the space-time continuum, because our spatial coordinates, x, y, and z, have to be combined with time, and gravity distorts it. That, turns out, was the solution to Mercury's orbit. It happens to all planets, but it was easiest to detect with Mercury because it's closest to the sun and it experiences the greatest warping because of general relativity. But it can happen other places. There's not much around the Earth, but there's enough that if GPS satellites didn't take that into account when they were triangulating positions, they wouldn't be able to pin us down, give or take 3 meters, like the commercial GPS systems can now. Now, without general relativity, they'd be off by more like 300 meters. So the technology we have now is that precise. So relativity is here to stay, or at least these features of it are here to stay. So now that we've talked about Mercury, we do have one other idea that was even more earth-shattering at the time. That'll be the topic of Part 5.